I'm going to do that. It's fine. Thanks.
That's a hard industry to listen to. Hard job.
Yeah.
It's just a video game writing. That's hard because they're like, okay, we're going to make the game first, right? Well, in America, it's this way. They're going to make the whole thing first, and then they're going to say, okay, now make a story based off of what you did. It's not write a story and then we'll make it based off of your super creative story. It's the other way around. So you have like a little tiny box in Asia. It's the other way around. You write the story and then the game evolves into the story. That's why like Japanese games have second stories, Final Fantasy, and stuff like that.
I thought that's 24th, right? Some 24th?
19.
On the syllabus it says 24th.
I know. There's the statement at the bottom that says, I reserve the right to change with reasonable notification to the student. 2 weeks is reasonable.
Oh.
Yeah, check that out. You always read the fine print.
Okay. So it was 24th. We have some day. We can practice during the weekend.
Okay. Then practice this weekend. You'll be okay. Trust me.
You changed the exam date, is that what it's?
Yes.
You moved it up in class, didn't
I
you?
did.
Is that because we're just that good, or because you don't want to fall behind?
Neither. It's just, generally what I found out is that if I wait too long after I've instructed material, people seem to do worse on it. So, and we're at a good pace to where we're not losing time and I'm not rushing through anything, so.
That's how it goes with anything. If you don't use it, you lose it.
That's true.
This is just the same thing that's on Blackboard, right?
Yep. Yeah. Because not everybody uses Blackboard. Yeah, all this is already on Blackboard, so you don't have to write it down if you don't want to. But like I said, for those of you that refuse to look at the announcements in Blackboard, at least I can say, well, it was on Blackboard and I put it on the board in class. So, what's that? Whiteboard, yeah. Yep. All lives matter.
There's a couple more colors.
There's not a chalkboard in here, so green lives matter. Whatever. Okay, so obviously this is what's going on. So, so I think we have to do 2 more indirect proofs, and then we'll be done with indirect proof. And then we're going to take a look at sequences and series, and we should finish up all that stuff today. So then on Wednesday and Monday, we're going to look at something called mathematical induction, which is our last type of proof that we need to go through. And then that should take us about a class and a half. And then for the other half of class next Monday, we'll review for the examination. Okay? And then probably what I'll do is I'll probably just post like a list of how the exam's going to go. But basically it's going to be like 10 2-point short answer questions, and then I'm going to have 6 proofs. So that's how the test is going to go. So I'll post it on Blackboard as it gets a little bit closer for you guys. Okay? And then for the assignments, next Monday assignment 6 will be due, and then the following Monday assignment 7. Okay, so we're getting there. So any questions, guys, as to what's going on before we get started? Okay, pretty straightforward. Okay, so one of the sneakiest and classical types of proofs that always occur in mathematics, and I think for those of you guys, if you're a pure math major, if anybody's actually doing that, this is something you guys might see in an abstract algebra or abstract math class. So it's a little bit sneakier proof, but I just want to prove that root 2 is irrational. And just because it's one of the most complex proofs, and if anybody ever looks in the book, you might have seen this, and it's a fairly intimidating proof. So I want to make sure that if I was to ask you guys to prove something like the square root of 3 is irrational, you guys can do that sort of thing. All right. Just like we did on Wednesday last week, anytime you have anything with an irrational number, use contradiction. It's the easiest way to go. Okay. So let's suppose not. So here's our proof. We always start our proofs that are by contradiction by suppose not. And hopefully this is really easy. guys, what's the negation of root 2 is irrational?
It's rational.
It is rational, right guys? So let's say suppose not, suppose root 2 is rational. And again, guys, the reason we utilize contradiction is because, especially for irrationals, is because we don't have a definition for irrational, right? But we do have a definition for rational. So what can we say about root 2 because it's rational, guys?
You can write it by A over B.
Sure. So by definition of rational, okay, so by the very definition of rational, we can say that the square root of 2 is equal to A divided by B. What else do we have to say
A,
with
B are
definition?
integers.
Okay, A and B are certainly integers.
And B
So
cannot
A and
be.
B are integers. We should certainly say that B is non-zero. And there's one other thing that we said about rational numbers that I said you'll never need to use it except for maybe 1 or 2 proofs. This is 1 or 2 proofs. So what's the only other condition for rationality? Anybody remember? They don't share something. It's okay. They don't share common factors. Okay? So, and that's going to be the contradiction that we're eventually going to run into in this proof. Now, every other proof, that's good there. So, thanks, Dan. Oh yeah, that would be helpful too, wouldn't it? So, thanks, Dan. So, we're going to say that A and B share no common factors. So now that we have this, okay,
Once again, A, B share no common factor. Is that for rational numbers? Or
correct, for rational
Okay.
numbers. Definition of rational means it has to be in lowest terms.
Okay.
Okay, so that's what A has no common factors. And again, that's going to be essential to this proof. Okay, so now that we know that they don't share any common factors, we could say that the square root of 2 squared is equal to the square root of A over B squared. Okay, that's true, right guys? Okay, nobody doubts that. And the only reason I'm doing this is just because I don't have anything else to work with at this point. And I'll fill in the steps as we go along with this. Okay? This is the same as saying that 2 is equal to A squared over B squared. Right guys? That's just by multiplication. Okay, that doesn't hurt anybody's feelings, hopefully. And then I guess what I could also do algebraically is I could multiply both sides by b squared. So I could say 2b squared is equal to a squared. Okay, so let me let you guys copy that down. We could just fill in the steps as well. We might as well go ahead and do that. So this is just by exponent rules, So, okay, so this is by multiplication, and this is by multiplication as well. All right. So, what can we say about a squared? Anything?
A squared is equal to square root of 2b, square root of
Yeah,
b?
we could say that. Okay, I mean, you're right. It doesn't help us, but you're right.
Oh, a squared. So a times
So what
a.
can we say about a squared? It could equal n. Well, what does it have a factor of?
2.
Which
Oh.
means it's, if something has a factor of 2, what does that mean?
Then it's not a
Then
rational.
it's even, right?
Even, yeah.
Okay, so what we're going to do is we're going to say thus a squared is equal to 2b squared, which means it's even by definition of even. Okay, so this is a really sneaky proof, by the way. Okay, so I'm just making sure, like as we're going through this, at the end of it, you'll see why we have to use this definition. Okay, so we're going to say thus a squared contains a factor of 2. And is even by definition of even. All right. Now, since a squared is even, can we say anything about A? A must be even as well. Okay, how do we know that?
That's the rule of even numbers, right?
We actually proved it, okay? Didn't we in class by contraposition? Or maybe we did the odd one. I can't remember what we proved in class, but I think we proved either last class or for homework, I asked you guys to prove that if a squared was odd, then a must be odd as well for all integers, or for a squared even. I think I might have asked you guys to do that for homework. So this was proved previously, okay? If I give you guys this proof on a homework, I'll give you that hint that you don't have to prove that again, okay? So since a squared is even, a must also be even. Okay? We'll just say proved previously. All right.
Do we have to say proof previously?
You could just say either that or by a hint if I give you a hint, okay? But you have to just make sure, like, you know, I mean, something like that. This would be its own proof. We would have to prove that by contraposition if I never gave you like a hint or anything like that. Okay. So, everyone good so far, guys? Any questions at this point? A little bit sneaky, okay? What does that mean about A then? Okay, so A would be equal to 2k, right? Because A is even, okay? So by definition of even, A is equal to 2k, where k is an integer. Okay, I like that. All right. So now that we know that A is equal to 2k, couldn't we substitute 2k back in right here for A squared? Okay, I mean that's basic substitution. So we go right here, back substitute. Okay, so by substitution, we can say that 2b squared equals A squared is going to become 2b squared equals quantity 2k squared. Okay, so all we did was we just substituted back in for A. And then I'm guessing you guys can figure out what to do next with this. So if I was to ask you guys what to do next, what seems obvious?
Multiply.
Yeah, just multiply it out and it becomes quantity 4k, or just 4k squared. So 2b squared is equal to 4k squared by multiplication. Okay. And then, so what do you guys think we might be able to do?
Divide by 2.
Yeah, divide by 2 maybe. Sure. I mean, we could divide by 4, we could divide by 85 if we wanted to, but let's divide by 2. So we could say that b squared is equal to 2k squared by division. Okay. So let me give you guys a minute to make sure that's all cool. Okay. And I haven't done anything, I don't think, too out of the ordinary at that point. Okay. So this is a little bit sneaky right here. Okay. So, any questions, guys, thus far? Mr. Rober? You're just making sure everything's cool? No question yet? Not yet. Okay. All right. So, what can we say about b squared, if anything?
It's even.
That it's even, okay? So, thus b squared contains a factor of 2. Contains a factor of 2. And is even by definition of even. Okay, well that's nice. Well, if b squared is even, okay, what can we say then about b? It must be even as well. And how do we know that, guys?
Proof previously.
Yeah, it's right here. We proved it before. Okay, so we had a hint. Okay, so thus, if b squared is even, b must also be even. And in parentheses, proved previously. I should actually say proved previously in this class. because for any of the proofs I give you, you could have said proved previously, but we don't know when they were proved previously, which is true, but it has to be proved in this class sometime. All right. So we got all this good stuff going on. Okay, so what? So we need to do a contradiction at some point, right, guys? I mean, that's the whole purpose that we're doing this. So have we arrived at any contradiction, or can we do any more substitution, or somebody give me something here so we can finish this off. So, Michelle? What's the common factor, Michelle? Yes, okay. Guys, the contradiction, okay, A must be even, right? So A equals 2K, okay? B must also be even, okay? Thus, B must be equal to 2P, where P is an integer by definition of even, right? Well, now what we see is that both B and A contain a common factor of 2 because they're both even, okay? So, thus, A and B contain a factor of 2. Now, why is it so bad that they contain a common factor of 2? Right, because didn't we say at the very beginning of the proof, we said that by the very definition of rationality, A and B must not share any common factors. So we finally come into a contradiction, okay? So that's the hard part of this, guys. The most difficult part of this proof, especially with contradiction, is sometimes you have to pull stuff out of nowhere to be able to derive your contradiction. And this is one of those types where you just have to go along with it and prove it out of nowhere. Okay? So, we could say that this is a contradiction. Since A comma B share no common factors. All right.
Well, since A and comma B are supposed to share no common factors, but the proof shows that.
Right, this is a contradiction because A and B should share no common factors. Let's say that.
Why did we use P again when B equals 2P?
Oh, just because we wanted to show that it has the form of 2 times some sort of value, okay? Because remember, Andre, we're trying to show that it contains a factor of 2, or is even in this case, okay? So it's just 2 times some integer.
That part's the arbitrary part.
Right. We don't really need to know too much about that. Okay? All right. Clearly it's a contradiction, so that means the negation is false and the original statement is true. Okay, so this is a contradiction, thus the negation is false and the original statement is true. Okay, so root 2 must be irrational. Right. Bless you. No other way to prove it. Go ahead.
Okay, since we already have shown that A has a factor of 2, and in the initial we declared that A and B should not share. So if we just showed A contains a factor of 2, we don't have to do all this stuff.
We still do, because we have to show that B contains a factor of 2 as well.
But it's and. And means if one is false, the whole thing is false, right?
No, we definitely have to show that they both contain a factor of 2. We don't know that for certain.
If you don't
No, what am I
B
saying
has
is,
a
he's
factor.
like, it's a A and B share no common factors. So, right, but if you use the terminology and, if one of the preposition is false, the whole outcome is false.
Right, but you don't know that B contains.
No, we already
a
know
common
that,
factor.
we already know A contains a factor of 2.
But we don't know that B does yet.
Right, yeah. Until you prove that B contains the same factor as A, you don't know that they both have a common factor.
Right. Like right here, we don't know yet that it has the common factor. Okay? That's we know that they shouldn't share common factors. All we're doing is we're showing that they eventually have a
share.
Right.
Okay.
So we're just, they should not share a common factor by definition of rationality.
So share means like they should have the like a same common factor or like.
They should, like for instance, okay, 3/6 is not rational because they both contain a factor of 3, right?
Uh-huh.
So when I say share, it means they both contain the same factor,
Okay.
okay? Does that make a little more sense now, Art?
Gotcha.
We don't know that for sure up here because we don't know what A and B necessarily are yet, and that's what we have to prove and go through and do this. Okay, does that make sense now,
Yes,
sir?
gotcha.
Okay, good. All right. Yeah, it definitely is sneaky, okay? And as you guys go along, not in this course, but in other courses, the other proofs get even sneakier than this.
Especially since most math classes don't say that A and B share no common factors.
Right.
They just say simplify it.
Correct. All right, so that's why I'm trying to show you guys these sorts of things. And sometimes something even as I guess, maybe unassuming as that becomes like the major component in the proof. Okay, so yeah, but when you guys get to your higher level math classes, make sure you guys, when you're doing proofs, make sure you don't discount any of the given information. Okay, now you guys know that we haven't used this yet, and I've said we're not going to use it until now. Okay. All right, for homework, I asked you guys to show that root 3 is irrational. And I give you guys the hint that if 3 divides a squared, then 3 divides a. So you're basically going to do the exact same thing, except instead of using even, you're just going to use divisibility for that. Okay? So if you guys get stuck with it, come to me on Wednesday. I can try to help you in the right direction with that. All right. Questions about this proof, guys? Definitely a more difficult proof than what we're used to. Okay? Now, a little bit easier is the next proof that we're going to look at. So this guy's pretty easy. Oh, Adam, I'm sorry, and then Ryan.
So at the end, when you're saying this is a contradiction because they should share no common factors,
Correct.
would it be okay to say this is a contradiction because A and B share common factors?
Correct, yeah, if you said like they share common factors because it contradicts this component that says they shouldn't, okay? So yeah, either way you want to do it, all you're doing is you're just pointing out that they have a common factor, okay? And we already showed it right there up top. We said that they both contain a factor of 2. So there's more than one way to write that ending. Is that how you're thinking of doing it? Which is perfectly fine.
I just want to make sure.
Oh yeah, sure, that's good, Adam. Okay, Brian, you have a question?
Can I get a factor?
Oh yeah, sure, that'd be helpful too. Paul passed to Andre, Andre passed to Ryan. There you go. Okay. All right, guys, other questions before we go ahead and finish up with this one? Okay, so the next proof that we have is a lot easier than the previous. Okay, this one says to prove that 7 minus 3 roots of 2 is irrational. Now, the good news is that we've already proved that root 2 is irrational. Okay, so you probably already think to yourself, okay, it's going to be irrational. Okay.
When we're doing something like the homework or on the exam, if there's a problem where we have to prove something like the square root of 2, can we use that in a following problem saying, oh,
And I would say
we already proved this previously in a different problem? Okay,
And what I would do is I would specifically spell out, you may use the fact that.
Oh,
Okay? So I'll do that. So now in real life, in another course, if you haven't proved it, you don't want to make that assumption. Okay? So you don't want to say to your teacher, well, I already knew that. And they're like, well, how do I know that you know it? Sort of thing. So,
okay.
so what you would actually have to do in another course, like if we were doing this proof and it was the first time we did it, we'd have to do a side proof. Okay? So,
Right.
And
Well,
that happens
the first time,
unfortunately.
yeah.
No,
No,
I
I'm
don't
just referring to using what we already have, or resources, I guess
Right.
I can call it.
In this class, I never make you guys do side proofs, okay? Once you prove something, it's one proof per problem, okay? All right, so here's our proof. Again, it contains a rational number. So, because it contains a rational, or irrational, we say suppose not. Of course, we're going to say suppose that 7 minus 3 roots of 2 is rational. So suppose not. Suppose that 7 minus 3 roots of 2 is indeed rational. Well, if it's rational, what can we say about 7 minus 3 roots of 2?
Factor of A over B.
Yeah, equals A over B. Okay, so by definition of rational, seven minus 3 roots of 2 is equal to A divided by B. And just like before, A and B are elements of the integers. B is non-zero. Now, we don't need the fact that they should not share a common factor. Okay, so for this one, you don't have to write that. Okay. All right. So, does anybody think they might know an approach that we could utilize, considering that we already just proved that the square root of 2 is irrational?
Since you're using the proof of the square root of 2 being irrational, you still don't need to mention that A and B.
Correct. We don't have to mention that they're
Because it's mentioned in that.
correct, because we've already proved it in the previous. Okay? So we're just going to use that fact. So, Donnie, did you have a suggestion?
Can you put like, can you change that to square root of 2 with another, like a letter?
Unfortunately, we can't say closure because it's not an integer value. Okay? So if it was just regular 2, then sure we could, but that square root just throws everything for a wrench. Good try. So, any other suggestions, guys? So, John?
We try to show that square root of 2 is equal to a rational number, like the contradiction.
So maybe solve it for root of 2 first, and then that might get us somewhere. I like that, okay? So if you guys were going to solve this for root of 2, okay, do you guys have a suggestion as to maybe how you would start that?
Subtract 7.
Yeah, subtract 7 from both sides. Nice job. So just by some basic algebra, we could say minus 3 roots of 2 is equal to A over B minus 7. Okay, so that's just by subtraction. We could get a common denominator and just meld this into a singular fraction, couldn't we, guys? So by common denominator, and like I said, I'll write the steps up in a moment, negative 3 roots of 2. If I was to write this as a single fraction with the denominator of b, what would the numerator look like, guys?
A minus 7b.
A minus 7b. The common denominator is b. A already contains a denominator of b. 7 needs the b. So a minus 7b divided by b. And then couldn't we divide both sides by negative 3 or multiply by negative 1/3, however you want to do it. So root 2 is equal to a minus 7b divided by minus 3b, right guys? Okay. And by the way guys, this is just all algebra stuff, okay? Nothing higher than algebra 2. So, but do those steps make sense, guys? Especially considering we've done rational stuff so far. And then because of all this, what can we say that root 2 must be equal to eventually? Yeah, like m over n, p over q, s over c, whatever you want to call it, right? So root 2 equals m divided by n, where m and n are integers. Okay, now let's fill in the steps here. Okay, so before we do that, is everyone okay with the algebra to this, guys? Any questions? Okay. The first step, all we did was we just subtracted 7 from both sides, so that's just subtraction. The next step, we just got a common denominator. It's technically LCD / subtraction. Okay, that's easy. And then this step was division. And then the very last step that we did, that's just our friend closure. Okay, so let me go ahead and let you guys copy that down. So this one was much algebraically less taxing than the previous proof, or hopefully it was. All right, so my question to you guys now is, well, how is that a contradiction? Well, what is root 2 equal to?
You already proved root 2 is irrational and you're showing that it's rational.
That's a contradiction, right? Okay, and I think John outlined that very nicely at the beginning where he said, let's solve it for root 2, let's show that root 2 is rational, even though it's not rational. Okay, does that make sense to everybody, guys? I think it's a good approach when you're dealing with irrational numbers. Solve it for the irrational, and hopefully it equals a rational number. Okay? So here's how we can close this out. We can say, thus, root 2 is rational by definition of rational. As Mr. Weber just said, well, that can't be possible because we just spent 20 minutes showing that root 2 was irrational, okay? Unless we lied to each other and it wasn't really rational, okay? But it is, okay? So we can say this is a contradiction since we showed root 2 to be irrational. We already proved that. Okay? And Andre, I think that's what you were talking about before. Can we borrow from something that we've already proven? And we certainly just proved that root 2 is irrational. Okay? So we start to have like this bank of things that we know are to be true. Okay? All right. So clearly, that means that the negation is false. The original statement must be true, meaning that this structure, 7 minus 3 roots of 2, is indeed irrational. Okay, I'll finish that up over here.
Realistically, when we're first starting the problem, I mean, if you just kind of do the math in your head, you know it's going to be irrational.
Yep.
So, is that sort of a good way to self-check by solving the problem first?
Oh yeah,
just
absolutely.
mathematically before you actually start?
You always want to see like which one's going to be valid, either the original or the negation. Because remember, only one of them's true. Okay. You can't have the original and the negation both be true. Okay. I think it's a great idea. Like just in your head say, okay, well if I have to use contradiction, which one of these is true? And if the negation's false, prove it false. Okay? And when I say prove it, like you just keep beating it up with algebra until you get to somewhere where there's a contradiction somewhere. Alright, so thus the negation is false, and the original is true. And we be done. Alright. I think for homework I asked you guys to prove something like 3 plus 5 roots of 3 is irrational. And you can use the fact that root 3 is irrational when you guys prove it, okay? Or if you don't prove it, you can just assume that you proved it, or got it really close to doing it. Okay. All right, guys. So, any questions I can answer about proofs that contain irrational numbers? Okay? Anytime you have irrational numbers, all you guys do is just use contradiction. Okay? It's the easiest way to go about it, okay? All right. So the good news is, for the rest of today, we're done with proofs. Okay, I'm sure you guys have been done with proofs for about, yeah, I know, good stuff. The bad news is on Wednesday we're going to come back to it. Okay, so I know. It's horrible that a math class would contain proofs in it, right?
Why not just switch them around so we finish those first?
Because unfortunately, to do induction, we need to know sequences and we need to know series. Okay, so it's basically like you can't do calculus 1 until you know how to factor a polynomial and basic algebraic operations. So guys, what we're going to do is we're going to start with just some basic sequence stuff, implicit, explicit forms, okay? But a sequence is just a list of elements with some pattern, okay? It doesn't have to be numerical, but for us, we've probably utilized like some sort of numerical sequences. Most of us are probably accustomed to arithmetic sequences. Arithmetic just means you keep adding a number to get there, but that's not the only type of sequence. There's geometric sequences, there's all kinds of sequences that we can try to look at, okay? In this class, we're going to stick to the two most basic ones, arithmetic and geometric, okay? There's first of all something called an implicit form and an explicit form, okay? And then there's a domain and an initial value. So every time you guys have a sequence, there should be four things that are going on, okay? Whenever we talk about the implicit form, okay, so the explicit sequence is just basically like where you can just plug in a number and then you get a number out of it, okay? It's almost like the functional form. So if you guys see the word explicit, you can replace that with functional. And you guys know what function is, one input, one output sort of thing, okay? The implicit form is where you list out the elements. Okay, so that's sort of like your set builder or your roster notation where you just list out the elements. So implicit is just the long form, it's not as useful. Explicit is the more useful form. And by the way, guys, every sequence has an infinite number of explicit forms. Okay, I want you to notice like this implicit sequence right here, 1, 3, 5, 7, 9. Those are all the odd numbers, right, guys, that are whole. And we know the definition of odd is 2n plus 1. So one way that I could define an odd number, if it was a positive, is that a sub n is equal to 2n plus 1, where n starts at 0. Because I plug in 0, I plug in 1, I plug in 2. Or couldn't I start at 2n minus 1, but start at 1? Because if I plug in 1 here, the output for that is 1. If I plug in 2, that output is 3, all right? What if I said the sequence a sub n is equal to 2n minus 5, okay? Couldn't I get that sequence, that explicit form, to give me that implicit form, if n started at what number? 3, right, guys? Because think about if you plug in 3. 2 times 3 is 6, 6 minus 5 is 1. Think if you plug in 4, 2 times 4 is going to be 8, 8 minus 5 is 3. So like I said, there are an infinite number of explicit forms that we could do for any sequence if you wanted to. Okay? So now our job is, if I give you the implicit form, okay, I want you guys to be able to write the explicit form of that sequence. Okay? Some of them are really easy, some of them take a little bit of brain power to be able to work with. Okay? So let's go ahead and try to work with these. Alright, so I want to write, instead of the, it should be an explicit form. So we can just change that to an explicit form, because there are a number of these, okay? Now please be nice to me while you guys are doing this. I know you guys can get really creative, okay? And instead of doing something like really simple, you can make it really complex, and then I have to sit there, and so try to be nice to me as you guys could, okay? But I just want to write an explicit formula for each of the following for each of the sequences. They're not alternating, so we can just cross out the word alternating for right now. Most of them are, but not. So let's start off with one that's really easy.
Now,
right?
is n starting at 1 over here?
Well, it doesn't have to. We define the domain.
Okay.
Okay? So it doesn't have to start at 1. And that's why I said there's an infinite number of implicit forms.
Okay.
So I have 1/2, 1/3, 1/4, 1/5, 1/6. So if I was to ask you guys to write an implicit form for this, okay? Can somebody tell me one implicit form for this, or one explicit form for that sequence?
1 over 1, n plus 1.
Okay, so we have 1 over n plus 1. But, or if we say that, where does n have to start?
1.
Okay, so that means that n is an integer, n bigger than or equal to 1. Okay? And think about that, guys. If you plug in the integers 1, 2, 3, 4, 5, 6, if you plug in 1, that gives you 1/2. If you plug in 2, that gives you 1/3. If you plug in 3, that gives you 1/4. So that implicit form, or explicit form, certainly satisfies that implicit form. Does that make sense, guys? Not difficult. What's another one that you guys could think of? There's certainly more, but it doesn't matter who wants to. Okay, so you can do a sub n is equal to 1 over n, where n is an integer, but n is bigger than or equal to 2. Okay, John, were you going to suggest a different, or say one? Okay, he stole it from your mind. It's kind of creepy. Right. Guys, there's an infinite number of those. Okay, it's whatever one you want to start with. Okay. Now, generally, the more simplistic that you can keep the sequence in terms of structure, the easier it's going to be to work with. Okay, so I always suggest, guys, that if you guys can write a more simplistic relation, it's probably better than a. Okay. Now, letter B is a little bit sneakier. Okay. Because notice that the signs are changing. Okay, and that's called an alternating type of sequence. Okay, some of you guys know that, some of you guys don't. But when the signs change, either negative, positive, positive, negative, and if there's like a one-to-one relationship between the parity, that's alternating. Okay, for those of you guys that have suffered through Calc 2 and sequences and series, you know that. If not, don't worry about it. Okay, what I always tell people is ignore the signs, and at the end of the problem, worry about the signs. So, if I was to just ask you guys to write an implicit form, or an explicit sequence for 5, 7, 9, 11, 13, there's a number of ways that we could do this, okay? So, does somebody think they can tell me one explicit sequence for that? So,
n plus 2.
Okay, so we could say n plus 2, providing n starts where?
1.
No, 5.
Nope. 3.
3.
Okay, so that's okay. So in fact, I don't think that would work. Because if we plugged in 3, 3 plus 2 would be 5. But what happens when we plug in 4? 4 plus 2 is 6, right? And 6 isn't going to be in this. So you're close. Okay.
Yeah.
Okay, there we go. So 2n plus 1 maybe?
Yeah, I mean,
Yeah, or 2n plus 3, or 2n plus 5, or 2n plus 99, right? It doesn't really matter, because we can do whatever we want. But where should n start if we do this, guys? 2, right? Because 2 times 2 plus 1 is 5. So, now hold on 1 second. Let me rewrite this because I'm going to need a little bit of space here. So we're going to say 2n plus 1, where n is an integer, n is bigger than or equal to 2. And guys, all you do is you just go back to check, and you plug in 2, you plug in 3, you plug in 4, and they should match up to those values, okay? Which they do, right? Except for the parity of odd and even, or for negative and positive. All right. Now, what we need to do is we need, because it's alternating, we need to throw in an alternating factor. So, does anybody remember like that factor that can help you toggle between positive and negative?
It was negative 1 to n plus 1.
Right. It could be either be negative 1 to the n or negative 1 to the n plus 1, right? So it's got to be one of the two. All right. Now, John, you used n plus 1, right?
Yes.
Because, well, guys, let's think about how that changes. Okay. What happens if you plug in 2? Oh, by the way, this should be in parentheses as well. Sorry about that. What happens if you plug in 2 into negative 1 to the n plus 1? Does it become negative 1 to the third? And guys, what do you know about negative 1 to the third?
Negative.
It's negative. What happens if you plug in 3? It becomes negative 1 to the fourth, right? Which is positive. And then it goes to 5, which is negative, and then to 6 to positive. So it has that alternating parity, okay? Quite honestly, we could have used n plus 1, n plus 3, n plus 99, whatever we wanted, right, guys? As long as it stays odd and even, that parity between the two, okay? So, and the reason that we wanted to use this one is because we wanted the first term to be negative, right, guys? So if the first term we wanted to be negative, we wanted to make sure that when we plugged in this number, the initial value, it makes that first exponent odd. Okay, because remember, odd, even is going to change the parity. Okay? Does that make sense to everybody as to why the negative 1 to the n plus 1 works? If you don't believe me, just make a table of values, and you'll see how it alternates between positives and negatives. All right. Now, what about letter C? Letter C is the exact same problem, except now the first term is positive and the second term is negative.
So you just use negative 1 to the power n. That's
sure, right?
That's
you can just use negative 1 to the nth power, okay? It's either going to be negative 1 to the n plus 1 or negative 1 to the n. Those are the only two that you should ever consider, okay? So you don't want to consider n plus 33 or 2n plus 55 or anything like that. It's either n plus 1 or n, okay? There's no other way to do it. And what you do is you plug in your number. If that one doesn't work, you use the other one, okay? So that's the easiest way to do it. It's got to be this one or this one. Those are the only two alternating factors that you guys should ever consider, okay? There are a couple other alternating factors, but you probably don't use them for anything. Okay, so let me finish this off. Like, just for fun, I don't know if you guys know this, but cos of n pi is an alternating factor as well. Because depending upon if n is even or odd, if you have cosine of pi, that's negative 1. If you have cosine of 2 pi, that's positive 1. So that's another alternating factor, okay? So you can actually write alternating sequences using trigonometrics, okay? So I don't know how many people ever do that, or if you were in Calc 2, if you ever saw that or not, or if you will see it. But I'm just letting you guys know, if you're ever in a math class and you see something like that, that's another alternating factor. And sometimes it's a sneaky one, okay? Sometimes if you want to go like negative 0, positive 0, negative 0, positive 0, I've seen this one on occasion. You guys don't have to write this down, by the way. I've seen this one. So where what happens is it starts out as, if you plug in 0, it goes to 0, and then 1, and then 0, and then negative 1. So that's another alternating factor, but maybe you only want some of the, every other term to exist. Like maybe if you had an odd function, you only wanted the odd terms to exist, okay? I don't know if you guys remember, but there is a way, like when you guys have heard the terms even and odd refers to its series expansion, okay? Because you can write functions as series sometimes. Is it an odd series? Is it an even series? So, like when you guys were pre-calc, even just means it's symmetric about y. Odd means it's symmetric about the origin, okay? And you guys didn't know why it was called even and odd, okay? So if anybody wants me to keep talking about it, I will, but I guess you guys just want me to get done. Sorry, I get all happy about that stuff. Sorry about that. All right, letter D is probably the sneakiest one, isn't it, guys? Because it starts with a negative, and then all of a sudden, the rest of the terms are positive, okay? So this one's really, really sneaky. So let's call this D sub n. Now this one's not alternating, so we don't need the -1 to anything. Okay? See if there's a relationship between the numbers. Now these aren't arithmetic, right? Guys, arithmetic means you can just add a constant and get to the next number. Okay? And we don't want to use recursion. We don't want to use the fact that you could just say, oh, okay, well the first time I added 3, and then I added 5, and then I added 7, and then I added 9, and then I added 11, etc. Okay? Because that's a recursive sequence. Okay? So we don't want to do that. So does anybody see like a pattern that's going on with those numbers or anything?
Square -2.
All of these numbers are 2 less than a perfect square, aren't they? Like for instance, 23 is 25 minus 2. 34 is 36 minus 2. 47 is 49 minus 2. Okay, nice spot. Okay. Even -1. Okay? Guys, what minus 2 is -1? 1, right? Which is a perfect square. So I think John. Oh no, it's not wrong.
No,
it's
I
right.
mean,
He's absolutely
it's
right.
wrong to put that kind of
Oh,
thing
but that's
up,
why
right?
we're doing it together. It is sneaky, sneaky, isn't it? All right. So D sub n. Mr. Duff, would you be offended if I wrote that as n squared minus 2, 2 less than a perfect square? All right. Now, of course, that's not complete just like it is, right? Because we need an initial value and we need a domain. So the initial value, and I'm guessing this is the one you would think of, John, would probably be n bigger than or equal to 1 to be able to start that. Okay, nice spot. All right. Yeah, that's a little bit difficult to see, okay? And that's why we do it together. So, because we're thinking, okay, well, what can I add to get to the next one, okay? Sometimes it's what can you subtract to get to the next. Okay, but these are all sequences, and as you guys can probably feel, especially in a computer field, isn't it more useful to have the explicit form rather than the implicit? Because it mirrors what type of data structure? Rhymes with array? Array, right? Because you can just index the number immediately, right? And in computer science, an array is one of the most powerful data structures that we have, okay? It can help you guys to sort things. It can help you guys to access things. It can help you encode things. You can do multi-dimensional arrays. So arrays are really cool data structures, okay? And basically, like, even like for those guys that remember what a struct is basically an array. That's all it is. Okay, it's just a more formal type. So anyway, sorry about that. Trying to make some connections for those of you guys that are computers. Like, why do I have to take math? I'm a computer science major, sort of thing. So that's why. All right. Anyway, more stuff. All right. Now, the difference between a sequence and a series. Okay, most people like say, oh, I know that there's a sequence and there's a series. But most people don't know the difference between the two. They're very similar, but they have one difference.
You add them.
You just basically add up the terms of the sequence to get a series. Okay? For those of you guys that are in Calc 2, you study infinite series. What happens when you add up an infinite term? Okay? So that's the difference between a sequence and a series. Okay? So, and for those of you guys that are in your Calc 2 and you're studying series, eventually you'll determine whether it's convergent or divergent, or hopefully you will.
The radius of convergence.
Yep, and then sometimes for a power series, there's only a specific domain of values to which that series is convergent upon, okay? And you go outside of that, then it bifurcates, or it just diverges. It does weird stuff, okay? If any of you guys are interested in chaotic dynamics or fractal geometry, fractals can diverge if they're based on a power series as well. So there's a lot of applications for infinite series. Okay? I love series. They're like one of my favorite fields of study. But anyway, obviously, because you could never tell that by anybody. Okay. Guys, when we look at this, basically for a series, most of you guys have seen this before. There's a lower bound and an upper bound. And then this guy right here is the sequence. Okay? So basically all you do is you just plug in the numbers and then you just evaluate. Okay, these are really easy problems, not meant to be difficult. Okay, at least the first one. So if I had, and I wanted you guys to evaluate this series, okay, the series from I equals 2 to 6 of I squared. Guys, what does that mean for us to do? Somebody just, go ahead, Don.
All the things from 2 to 6 and you add them together.
All the integers, right, sir? Right. It's not because we want, that's good. And I just wanted to make sure that everybody knew, like when you said things specifically, and I knew you knew what it meant. Okay. So Donnie, would it be okay if I wrote it as 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, sir? Okay, that's all the integers between and inclusive of 6 and 2. Okay? At this point, guys, we just add it up, right? So this is a really easy problem. Okay, we just go through and add it. So we get 40, and then we get 25, so it's 65 and 25. Is it 70? Or 80? 80, sorry. I was getting there. I forgot to carry one. So that's just 80. Okay. So literally, guys, a sequence would just have commas. A series has the plus sign. So that's the difference between a sequence and a series. Okay? All right. Now, unfortunately, if you look at letter B and you try the same method, well, what happens if you do that? Yeah, you're just going to sit there for freaking ever doing the
Don't you have
problem.
that Gaussian method, like the first term, last term, divide by 2, then the multiply by the number of terms?
Well, that is true. There's a closed formula for an arithmetic sequence.
Okay.
But this is not arithmetic because it's squared. Arithmetic means, like, for instance, 3, 6, 9, 12, 15. They're separated by a common difference. So that's where you would use that formula. Okay? So don't try to overextend those. Okay? It's good that you knew something, though. That's better than Congress. All right. So, like we said, guys, if we tried to do it by hand, we'd be here forever, right? We could use our calculators, but it says do it without a calculator, so that contradicts that. So here's my suggestion, guys. For something like this animal, maybe what we could do is just start listing out the terms and maybe see if something good happens. Let's hope it does. Okay? So let's just go ahead. I'm going to plug in 1, I'm going to plug in 2, I'm going to plug in 3. So if I plug in 1, this becomes 1 over 2 minus 1 over 1. Okay. Plus, I'm going to plug in 2, so that's 1 over 3 minus 1 over 2. Plus, so I'm going to plug in 3, I get 1 over 4 minus 1 over 3. Plus, I'm going to plug in 4, 1 over 5 minus 1 over 4. So all I'm doing there, guys, I'm just plugging in n equals I equals 1, I equals 2, I equals 3, I equals 4. Now that pattern would continue, right, guys? It would just keep going on indefinitely until we got up to maybe 100,000, or I'm sorry, 10,000. Yeah. So let's just go ahead and plug in 9999 and then 10,000. So this becomes 1 over 10,000 plus, or minus, excuse me, 1 over, or minus 1 over 9999. And then finally, plus 1 over 10,001 minus 1 over 10,000. Okay. So all I did there, guys, was I just wrote out maybe the first 4 terms and then the last 2 terms. Okay, so let me give you guys a minute to copy that down, because there was a reason I did all that stuff, I promise. It's not just to torture you all.
We had the problem in Calc 2. I remember it.
Yeah, this is a very common type of problem that you guys might have seen in calculus too. Okay? And some of you guys are noticing what's going on here. So somebody tell me, guys, why did I write out maybe the first 4 or 5 terms of this?
To get a pattern, the negative, like half and half cancels out, 1/3.
Because what we'll notice is that we have a positive half and a negative half, right, guys? So they go away. We have a positive third and a negative third. We have a positive fourth and a negative fourth. Guys, wouldn't the next term, even though we didn't write it out, wouldn't I have a positive fifth and a negative fifth, right? So these guys just all cancel out. In fact, doesn't the pattern continue at the very end, okay? Because I have a positive 1,000 or 1 over 10,000, a negative 1 over 10,000. This guy would cancel out too, wouldn't it? Because before that, in the previous term, there would be a positive 1 over 9,9999. Okay? Well, after all of that, don't I literally just have negative 1 from right here plus 1 over
10,001.
10,001, right, guys? And if I wanted to combine those, I'd get a common denominator. So I would get negative 10,001 over 10,001. Or in other words, this would just work out to be negative 10,000 over 10,001. Okay? Now, that very rarely works in real life, but of course we're in math life, so I can just make up problems that they do work. Okay? Maybe some of you guys have seen this before, it seems like, or you might have remembered it. But does anybody remember, that's a specific type of series. It either starts with an S or a C. Does anybody remember the name of it? What is it? Telescoping series. That's all right. You know what, Alex Trebek will take that answer. Judges say good. Yeah, that's something called a telescoping series, where inside the terms cancel out, okay? And this is one for those of you guys that are going to take Calc 2, you might have to build a telescoping series by doing partial fraction decomposition. Oh, lovely stuff, right? So this is something called telescoping. There's another name for it, starts with a C. Sometimes it's called a collapsing series because, and obviously you can see that inside it just sort of, it's going to self-contained implode. So telescoping or collapsing. Collapsing, yeah. Collapsing, yeah. I always call it telescoping because it sounds a lot cooler. So, all right. So guys, any questions? If I were to give you guys one of each of those on your homework, you guys would be able to do those to where you guys could just collapse the terms. I'll probably give you guys one like that on the exam as well. Okay, Adam, go ahead, sir.
I answered that A is supposed to be 90, not 80.
Okay, so this is going to be 40, and then this will be 25, and then so 40. I'm sorry, it's 40 and 25, and then 25 and 1. Yeah, you're right. It is 90. Usually when I can add correctly, but just write it on the teacher evaluation. Teacher cannot do simplistic addition. Sorry, way beyond my abilities. Yeah, sorry about that.
Series, that's funny.
Yeah.
Or the telescoping series.
I could prove if an infinite series is convergent or divergent, but if you ask me to do arithmetic, nah.
We're screwed.
Yeah, oh yeah. Boy. All right. Other questions besides my inability to add whole numbers? Sorry, Ad, but at least you gave me the bitch slap and put me in check, so I appreciate that. All right. Another idea that I want to look at that we're going to have to utilize when we do our proofs by induction is something called a change of variable. Okay, these problems are actually really easy. Okay. Like I said before, guys, it's always easier if you can write your series or your sequence in a simplistic form. Okay? Now, sometimes what we can do is we can take a series that looks ugly, okay, like some of the ones that we have, and just change the index, okay? Maybe some of you guys have done this in computer science where you had an array, and you basically just changed the place where it starts, and you got a new array that was a little bit easier to work with. Maybe not. I don't know if you guys have done that or not, okay? But I just want to show you guys some examples of where we have a series, and we just use a change of variable, and then we go ahead and get something a little more simplistic, okay? So, I have this first summation or series here, I equals 4 to 35 of I plus 3 over I squared. And I want to make the change of variable j equals I plus 3. Okay? Now, is it not true, guys, that if j equals I plus 3, I would have to be equal to what then, guys? J minus 3. Good. So we can just subtract 3 from both sides. Good. So this implicitly means that wherever I see an I can plug in j minus 3. Okay, so I replace j's with I plus 3. I replace i's with j minus 3. So let's just go ahead and substitute. Okay, so I'm going to rewrite the series. So now instead of having an I for the lower bound, we have a j. Okay, instead of going from 4 to 35, what should be the lower and upper bound respectively?
7, 38.
Other way around. Oh, wait. No, you're right. So we plug in 4 right here. You're right. I'm sorry, John. So we plug in 4 right here. So this would be 4 plus 3. And then for the upper bound, that would be 35 plus 3. Because we said that j equals I plus 3. Nice. Does that make sense to everybody, guys? We're just plugging in the lower and upper bounds back into our substitution. In the numerator, wherever I see an I, I'm going to replace that with j minus 3. So I would get j minus 3 plus 3 divided by quantity j plus 3, or sorry, j minus 3 squared. Okay? So really, guys, when we do a change of variable...
No, on the why did you do j minus 3 plus 3? You can just write j, right?
Oh yeah, I just want to make sure when people go home, they remember, how did it just become j? Where did the 3's go?
Okay.
Okay? So I'm just saying that wherever we see an I, we plug in a j minus 3, okay? But yeah, we're going to simplify this. And so Mr. W, you correctly identified the lower bound to be 7 and the upper bound to be 38. Okay. And then the numerator, j minus 3 plus 3 becomes j. The denominator just becomes j minus 3 squared. Okay, now, I don't know if that's any better looking than the previous, okay? But these two series mean the exact same thing, okay? Maybe for some reason you want the numerator to have one term because it's easier to work with, okay? So that's what we're doing with this. We're just rewriting it so that it's in a little bit easier or a different form to work with, okay? So does that make sense, guys? Any questions? Okay. The next one just as easy, okay? What I'm going to do is I'm going to start by solving for for I. So it would be clear that j plus 10 is equal to I. So all we do is just add 10. Wherever I see an I, I'm going to replace that with j plus 10. Wherever I see a j, I'm going to replace that with I minus 10. Okay, so since I is equal to negative 9, I'm just going to plug negative 9 back in right here. Okay, so j is going to be equal to negative 9 minus 10 to n minus 10, and then we have to also include for the other minus 10. So all I'm doing, guys, is I'm taking this and I'm plugging it back into this I right here. Because remember, the lower and the upper bound are still representations of the index I. Okay, so this is going to be n minus 10 minus another 10. Does that make sense to everybody, guys? All we're doing is we're just plugging this back in. So we plug in the lower and the upper bounds back in there. And then for the rest of it, wherever I see an I, I'm going to plug in j plus 10. So this is j plus 10 minus 10 squared. J plus 10 minus 9 cubed. And by the way, you don't have to go through all of that. If you can just go right to the answer, that's fine. I just want to make sure that for those of you guys that haven't done your change of variable yet, involving sequences and series, that this is how you guys might have to do it. Okay. For our answer, series j equals negative 19 to n minus 20. And then we just get j squared times j plus 1 quantity cubed. So any questions I can answer for you guys about what a change of variable is or how we might implement it? It's really just substitution, that's all it is. Okay. I might have asked this question before. I know some of you guys have taken differential equations. How many of you guys remember or had done that? Okay. What I remember is actually using this when you do the series solutions. Do you remember doing the series solutions, Don? It's like one of those things like, you know, you don't want to remember as a child. Like for me, there was an old show called Tic-Tac-Toe, and there would be like a dragon that comes up if you get 3 in a row, and I was terrified of that, and I was terrified of the vacuum. I felt like a cat when I was a kid. But so those are my memories as a kid. So that's why I ended up being a math teacher. So all of my fears I could instill upon you guys. Yeah.
You had a wonderful childhood.
I did. I definitely did. Yeah. So I remember Tic-Tac-Toe. I was afraid of Wink Martindale. Seriously, like the worst game show host ever. All right. The next thing I want to look at this afternoon is I want to look at factorials. Okay. A lot of you guys probably know what a factorial is, but if not, no big deal. They're fairly tame. Okay. Whenever you see n exclamation point, that doesn't mean that n is happy or anything like that. In fact, n is just a factorial.
Do you have to scream n?
Yeah, it doesn't mean like scream it out or anything like that.
It's enthusiastic.
It's somewhat enthusiastic, yeah. Actually, it gets really big really quickly, so maybe it is enthusiastic. So whenever you see n factorial, that's just n times n minus 1, and you just keep multiplying in descending integers until you get to down to 1. I should note that, and I didn't write this, but n should be an integer. Okay? Although I remember when I was, there is something called a half of a factorial. I remember when I was in integral transforms, we actually proved like what a half of a factorial is. It's completely useless, but I mean, that's the only thing I really remember.
Another thing, zero's factorial is 1.
What's that?
Zero's factorial is 1.
Right, 0 factorial is 1. Okay, so if you ever ran into that,
You didn't write that, yeah.
yeah, 0 factorial is 1, if you ever run into that. If you ever have to suffer through a statistics class or a probability class, that'd probably be a place where it's useful. For our class, it's not going to be useful.
The birthday thing, right?
What's that?
How many people share the same birthday?
Oh yeah, like the birthday problem, like the probability is like if you're in a room, the probability that you probably share a birthday is pretty high, believe it or not. Alright. So let's just go ahead and evaluate or simplify some of these and then we can be done with this stuff. Okay, and let's try not to use a calculator. So I have 5 factorial. Okay, so 5 factorial is just going to be expanded. That's 5 times 4 times 3 times 2 times 1, right guys? Okay, that's all a factorial means. Just multiply in descending integers until you get down to 1. You don't want to go to 0 because, well, then it just multiplies to 0. Okay. If we do this by hand, 5 times 4, that's going to be 20. 20 times 3 is 60. 60 times 2, 120. Although, I don't know if you want to believe me, since apparently I can't add. Oh, but this is multiplication, so I guess it's okay. All right, thank you, sir. I appreciate it. All right. Guys, does that make sense as to what a factorial is? It's not difficult. Okay, you just multiply in descending integers. Now, for item B, now this one's a little bit more difficult. 18 fact over 16 fact. Now, if I asked anybody in class what 18 factorial is off the top of their head, they'd look at me like I had 19 heads, because 18 factorial is just a ridiculously huge number. In fact, your calculator might just spit back the scientific notation of this, right? So if anybody tried to figure it out, it's just ridiculously huge. But I asked you guys to compute it by hand, which makes things even worse. Go ahead, Don. No, tell me something.
So if the numerator will cancel up to 16, all you gotta do is do 18 times 17.
Yeah.
Very good.
Yeah, because isn't it true, guys, that the definition of 18 factorial would be 18 times 17 times 16 times 15, all the way down to 1, right, guys? The definition of 16 factorial would be 16 times 15, all the way down to 1. And Don, you suggested that everything from 16 down to 1 are just going to cancel out, right? Because we're dividing them, okay? So it's not a collapsing series necessarily, because it's not a series or a sequence, but it's a collapsing form of something. So really, guys, aren't we just left with 18 times 17? If we really had to do it by hand, we could, okay? But of course, we're lazy, so we're just going to stick it into our calculators. Although 18 squared is going to be 324, so 324 minus 17, that's going to give us what, I guess 307? What's that? Oh yeah, minus 18, so that would be difficult. So that would be 306? No?
Yeah.
Okay, there we go. Thank you. Oh, you cheated. That's okay.
I had no idea what 18 squared was.
Oh, that's okay. Neither did I was just making up shit. I have no idea. Although you are right, I probably should subtract the right number.
Yeah, that would help.
Yeah.
With multiplication, that's
Yeah, I did okay with the multiplication, but then when I do addition and subtraction, I screwed that up. So once again, again. Okay. Does that make sense, guys? If I give you guys bigger numbers, easy to manipulate. Okay. What if I just have variable stuff? So let's say, for instance, I had n plus 4 fact, and I divided that by n plus 2 fact. Okay. Now, regardless of what the value of n is, we can still simplify this. In fact, we kind of already know what's going to happen with this, because isn't this the exact same sort of thing, where we have 2 more terms or 2 more factors in the numerator than the denominator? But we want to simplify this. So if I was to ask you guys to expand n plus 4 fact, okay? The first factor is n plus 4. What's the next factor?
N plus 3.
Right, because we just go down 1 integer. So it would be n plus 3. Next integer down would be n plus 2. Next integer down would be n plus 1. And that would keep going 1 until we got to 1. Right, guys?
Now, wouldn't it be okay to just put in n plus 2 with the factorial
Absolutely.
next to it. And
Correct.
right over.
Because this animal right here is really just n plus 2 fact. Right, James? Okay. So if you can see that, that's fine. Okay? And some of us are really good at seeing factorials, but some of us have never worked with factorials before. So I just want to make sure that if you've never worked with a factorial, that's how you work with it. The denominator, n plus 2 times n plus 1, 3, 2, 1. Okay? And clearly, all this stuff is going to cancel out, right, guys? So we're just left with n plus 4 times n plus 3. And if we really wanted to, we could FOIL that out, right, guys? So if we FOIL it out, we would get n squared, 4n, 3n is 7n, and then 12. So n squared plus 7n plus 12. And the good news is none of those are like terms, so I don't have to add them together, which means I can't make a mistake on.
But Chris, you have to remember, multiplication is just addition, repeated.
Don't make me feel any worse than I already do. All right. Does that make sense, guys? When you guys are in your Calc 2 class, you guys might remember seeing like your ratio test, and you probably did this a lot on the ratio test. Okay. Let's just do our last one here, and then we can be done with this stuff. So we have n fact over n minus 2. So we have n fact over n minus 2. Oh, by the way, if you've never taken Calculus 2, I know I keep referencing Calc 2 because this is the place where you might most likely see this. I'm not trying to exclude people that haven't taken Calc 2. I just want to let you know that it is used for something, and for those of you guys that have taken it, I'm just trying to make as many connections as I can. Okay. So let's expand the numerator and expand the denominator. Okay. If I was to ask you guys the definition of n factorial, well, we know that. That's n minus 1, n minus 2, all the way down to 3, 2, 1, right, guys? Because we just continuously subtract 1 each time we go down to the next integer. Okay. What about the definition of n minus 2 factorial? That's n minus 2 times what, guys?
n minus 1.
n minus
1.
Nope.
Minus 3.
3.
Right. Because remember, you're going down. You're going away from it.
Okay.
Okay, does that make sense? All right?
Yeah.
Okay, so don't ever do that again, please. Okay. Times n minus 4, all the way down to 3, 2, 1. So, is that okay with everybody, guys? Any questions about how to simplify that animal? Okay. Obviously, everything from n minus 2 all the way down to 1 is going to cancel out. So we're left with n times n minus 1, otherwise known as n squared minus n. And again, no like terms, so I don't have to make any errors. But I either try to multiply or repeatedly add or whatever. Okay. Guys, this makes sense about factorials. Not meant to be difficult. Okay. These are like the types of questions I like to answer, like those 2-point questions that'll be on the next exam, like the quickly stuff. Okay. All right. So you guys can work through everything that's on assignment number 6 right now, but it's not going to be due until next Monday. So my suggestion would be go ahead, get a head start on that, especially the proof problems at the beginning. Try to knock those out, and then if you guys want on Wednesday, I can certainly answer some questions. Okay? All right. So if you guys have questions, stick around. If you don't have any questions for me, then I would be happy to leave a little bit early, as I'm sure you guys are. All right. And then next time we're going to go